السلام عليكم ورحمة الله وبركاته رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي ربي يسر ولا تعسر وتمم بالخير. So in this video we will continue our topic of the DC machinery fundamentals. So today we will be looking at the solutions to the problems with commutation in real machines. So basically there are three approaches that have been developed to partially or completely correct the problems, but obviously every solution has its own merits and demerits. So let's look at them one by one. So as we know that we have the two commutation problems. One is the armature reaction and the other one is the LDI by dt voltages. So let's look at the first solution that we can use to reduce these problems. So first one is the brush shifting. So as the name suggests that when the uh, when this neutral plane phase shifts, actually, as we know that in the motor that's in one direction and in the generator it's in other direction. So whenever it shifts, this neutral plane shifts occurs, so we can also shift the brushes. So the first attempt that was the first attempt to made in the real DC machines to reduce the sparking at the brushes caused by neutral plane shifts and LDI by DT effects. So the first approach taken by machine designers was simple. If the neutral plane of the machine shifts, why not shift the brushes with it to stop sparking? But this method is good, but there are still problems. And what are the problems? That the neutral plane moves with every change in load, and the shift direction reverses with the machine goes from motor operation to generator operation. So therefore someone must adjust the brushes every time the load changed. So physically this was not possible that we can make these brushes that change the direction with every time the load is changing. So somehow we can put them in one direction permanently, and they can be used as the motor in a way means effectively, but not as the generator. We cannot we means if we use that motor as a generator, there will be a huge sparks in the motor in the generator if we use this machine as a generator. So that was the issue, that we cannot shift them with every load. So sometimes these brushes are shifted around the 70% or like this part of the way of the maximum rated load, so that motor can be operated somewhere at that part means for most of the time. So this is actually this is how we can see this is the old neutral plane, and we know that this is the new neutral plane with the when we have the load on the motor. So but there is some problem with also this, that even it have stopped the brush sparking, means not completely, but most of the sparking was removed. So but it also aggravated the flux weakening effect of the armature reaction in machine. So because the flux bunching, we cannot reduce that, and we know that the flux weakening occurs because of the saturation of the flux at one side of the pole, and then on the other side of the pole the flux was reduced. So these flux reduction, actually, as we have seen, that also caused the problems, that we cannot have the required torque to run the load. But also obviously we have some benefits of it, but that is for the time being are not major our concern, because we are for now concerned about the to to carry the load of or the rated load on the motor. So the change in armature current distribution causes the flux to bunch up even more at a saturated parts of the poles. So this is how that at the neutral plane phase at normal position that it occurs, that we have the rotor magnetomotive force and then we have this net magnetomotive force. So the net MMF in a DC machine with its brushes in the vertical plane. So what happens that the net MMF in a DC machine with its brushes over a shifted neutral plane, there is a component of the armature MMF directly opposing the poles MMF. So the net MMF in the machine is reduced. So here we can see that this net MMF will be reduced. Now here this was the original magnetomotive force, and obviously they are orthogonal, and we can have the maximum net magnetomotive force. But if we have these neutral plane phase shift and the brushes are shifted to the new location, so our net magnetomotive force will be reduced. That's causing the flux weakening problem in this motor. So there was another problem. Why not put another poles are called the commutation poles or the interpoles? So that commutation poles or interpoles will act as means they will produce the voltage in opposite direction that is produced in the brushes, so that that can be cancelled out properly. So the basic idea here is that if the voltage in the wires undergoing commutation can be made zero, so then there will be no sparking at the brushes. So to accomplish this, small poles called commutating poles or interpoles are placed midway between the main poles. So these commutating poles are located directly over the conductors being commutated, means between the gap of the, means I will show you here. So these interpoles are placed around here, because these are our main poles, north and south, that we can use, and here we will place our interpoles or commutation poles. So these commutating poles are located directly over the conductors being commutated. So by providing a flux from the commutating poles, the voltage in the coils undergoing commutation can be exactly cancelled. So if this cancellation is exact, then there will be no sparking at the brushes. So obviously, how we can make the voltage equal? So we can give the same voltage that we are giving to the motor. So the commutating poles do not otherwise change the operation of machine, so because they are so small that they affect only a few conductors about to undergo commutation. So notice that the armature reaction under the main pole faces is unaffected, since the effects of the commutating poles do not extend that far. So this means that the flux weakening in the machine is unaffected by commutating poles. So we have obviously we have now introduced new poles. So obviously it will be a costly solution, but we have the better operation of the DC machine. The third one method is to use the compensating windings. So for the heavy severe duty cycle motors, the flux weakening problem can be very serious. So to completely cancel armature reaction and thus eliminate both neutral plane shift and flux weakening, a different technique was developed. So in this technique, we place compensating windings in the slots carved on the faces of the poles. Means if I show you here, so we will carve here and we put the compensating winding on these poles. So this technique actually involves placing compensating windings in the slots carved on the faces of the poles parallel to the rotor conductors. So to cancel the distorting effect of armature reaction, so these windings are connected in series with the rotor windings, so that whenever the load changes in the rotor, the current in the compensating windings changes too. So by this technique, obviously it's a very expensive technique, because we have to carve means we have to make the carves in the on the face of the poles. So it actually costs more, but it is mostly used in the large machines, where we cannot bear the problem of flux weakening. So I hope you have somehow understood the basic solutions to the problems with commutation in real machines. So once again, if we recap it, so we have made these three techniques. One is press shifting, commutation poles or interpoles, and compensating windings. So for every technique, we have seen that they have their own merits and demerits, whether they are in the form of their price or their difficulty level to establish them or to make them in the machine. So still, if you have any questions, please feel free to ask. Assalamu alaikum wa rahmatullahi